Hi, good afternoon. This is Nitin Gupta from Attero Recycling, India's largest electronic waste recycling company and the world's best lithium and battery recycling company. Welcome to the Global EV Conference, and thank you for sort of inviting us to speak at this EV conference and sort of put forward our views on the opportunities and the challenges that exist in the lithium and battery ecosystem at this point in time. Without any further ado, I'll directly delve into the topic. So today, what we are seeing is there is a huge sort of opportunity in the lithium and battery ecosystem across various value chains, right? And going forward, we'll describe each of these and where these opportunities exist. But specifically, lithium and batteries are ubiquitous in nature. They are becoming more and more sort of prominent in, let's say, consumer electronics, whether it is mobile phones, computers, laptops, what have you, even stationary storage, whether it's solar storage, whether it's telecom towers and other forms of stationary storage, and increasingly in electric vehicles as well, whether it is two-wheelers, four-wheelers, three-wheelers, buses, trucks, what have you, right? The reason that lithium and battery is the dominant battery technology today, there are a few reasons for that. First, it's got the highest energy density compared to other battery technologies that exist. It's got the fastest charging time and it's got the slowest discharging time, right? So those are three critical reasons on why lithium and battery technology is far ahead of competing battery technologies that exist today. The more important financial reason is that more than $100 billion have been invested in the lithium-ion ecosystem over the last few years, and many more investments are happening as we speak, whether it is in creating gigafactories across the world, or is in creating battery packs across the world, or creating more recycling facilities, depending on which sector you are looking at. Uh, Specifically speaking about recycling, the the fact that lithium and batteries are becoming ubiquitous basically creates two large issues. First is that the what happens to the end of life lithium and batteries when they become end of life. They're hazardous in nature and need to be disposed of in an environmentally friendly manner, just to ensure that there is no soil pollution, there is no water pollution, there is no air pollution by improper disposal or unscientific recycling of end of life lithium and batteries. Second, from a cost perspective, almost the 50% cost of a EV is the cost of a battery, right? Out of which at least 30% is the cost of metals that make up the lithium and battery, which include cobalt, lithium carbonate or lithium hydroxide, manganese dioxide, nickel, sort of copper, aluminum, etc. Or graphite for that matter. Each of these metals has significant ESG issues along with supply security issues. Take cobalt as a case in point. Almost 70% of the world's cobalt is mined in the DR Congo region, which is driven by child labor, terrorist regimes, what have you. And at the current known sources of cobalt and the current utilization rates, the world will run out of cobalt by 2030, right? Similarly, lithium. Almost 60% of the world's lithium is mined in the Bolivia Argentina triangle, which, by the way, is also considered the world's driest region. The reason is that traditional lithium mining is a water guzzling process. And just to give you some context there, to extract 1 ton of lithium using a traditional lithium mining process requires more than 500,000 gallons of water, which causes whole amount of social issues and ecological issues in that area, right? So coming back to that point, each of these critical battery materials has significant environmental social issues, which is ESG issues, and supply security issues, right? So looking at it from this perspective, the very fact that we can collect end-of-life batteries, recycle them using an environmentally friendly process, extract the maximum amount of battery grade materials, which is cobalt, nickel, lithium carbonate, manganese dioxide, copper, aluminum, and put them back in the supply chain seems like a solution whose time is right at this point in time, right? And that's extremely critical, and that's why the lithium and battery recycling industry is gaining prominence as we speak, right? For a successful lithium and battery recycling industry, there are two key levers. The first lever is reverse logistics. How do you ensure that you collect all of these end-of-life lithium and batteries from consumers, from businesses, and ensure the lowest cost of collection at the lowest cost of compliance as well, right? And second is from a technology perspective, how do you ensure that the batteries that you collect back are recycled in the most environmentally friendly manner and with the most technologically advanced manner to extract all the battery materials and put them back in the battery supply chain, thus completing the circular economy supply chain, if you will, right? Where we are today, specifically from an Attero perspective, is we are running a commercial lithium and battery recycling plant in India, which we are expanding, by the way, where we collect all kinds of lithium and batteries. We extract pure battery grade cobalt. We extract pure pharmaceutical grade lithium carbonate. Lithium carbonate is actually used in the pharmaceutical industry in medicinal drugs to reduce the activity of the brain in various forms and shapes, right? And our current output of lithium carbonate goes back into the medicinal industry. That's the beauty of technology, right? And we're extracting battery grade manganese dioxide, we're extracting battery grade nickel, battery grade copper, aluminum that we are today sending back in the circular economy, right? The extraction efficiency of Attero's lithium and battery recycling technologies and process today is more than 98%. What that means is that if in the incoming end-of-life batteries there is 100 grams of cobalt or 100 grams of graphite or 100 grams of lithium or 100 grams of nickel, we extract 98 or more grams of cobalt, more than 98 grams of graphite, similarly more than 98 grams of lithium carbonate, more than 98 grams of nickel and copper aluminum, and that's extremely high. And we have 20 plus granted global patents on lithium and battery recycling technology developed by us in India and commercialized. The patents are in US and Europe and many more applied for. World over, from a technology standpoint, today the world is sitting at roughly around 70% extraction efficiency or below, right? And there are two dominant buckets in which technology for lithium battery recycling is happening today. The first bucket is a pure metallurgical operation where you take these end of life lithium and battery cells and put them in a smelter. A smelter is like your microwave oven, but on a larger scale with a much larger temperature profile, if you will. And let's say one company that is doing that today is Umicore in Belgium, right? Because lithium has a very low melting point, it gets lost in slag, right? Similarly, graphite is not recoverable using a smelting process. So the companies who follow a metallurgical recycling approach to end-of-life lithium and batteries are only able to recover cobalt and nickel. And Umicore, for example, recovers 90% of cobalt and nickel and does not recover lithium, does not recover graphite, right? The other sort of approach to recycling lithium and batteries is a pure chemical approach where you take these end-of-life batteries and pass them through various leaching, electrowinning processes, basically chemical processing, and extract cobalt, nickel, lithium carbonate, graphite, and others. In the chemical processing industry for lithium and battery recycling today, globally, the extraction efficiencies are around 50% for cobalt, nickel, lithium, right? And again, nobody is recovering graphite as we speak, apart from Attero. So that's where the market stands. The reason why it's so complex to recycle lithium and batteries and do it in an environmentally friendly manner with the highest recovery efficiency is that all these metals have their own metallurgical profile and chemical profile. But when they're mixed together, their properties change and they influence each other's properties. And some of these metals come from the same range in the periodic table, so it's very difficult to separate them and really requires a very advanced cutting edge technology, which is what Attero has developed, right? So that's where the market is, that's where we as a company are. And it's extremely important that this gets scaled up and put back in the circular economy. So there's a significant, meaningful impact that recycling as an industry can have on the lithium and battery ecosystem. According to our own plans, in the next few years, we'll end up becoming a significant player in the global lithium and battery ecosystem, supplying close to around 15% plus of the world's cobalt demand, supplying close to around 10% of the world's graphite demand, supplying close to around 12% of the world's lithium demand, purely by recycling, right? And that's the reason we call it urban mining. We're not digging up the earth to mine the metals that are used in lithium and batteries like cobalt, graphite, lithium, nickel, copper, etc. But we're using the end-of-life batteries, recycle them in an environmentally friendly manner, and putting them back in the battery supply chain. That's why it's called urban mining, right? Attero is also the only electronic waste and lithium and battery recycling company globally to generate carbon credits per ton of battery recycled or per ton of electronic waste recycled. So UNFCCC, the nodal body under United Nations, looked at our processes and agreed that, for example, the amount of energy involved to extract 1 gram of copper by recycling using Attero's recycling processes is significantly lower than the amount of energy involved to extract the same 1 gram of copper using either a virgin mine or any other known secondary processes today, right? And that way, not only are we recycling the end-of-life lithium and batteries in an extremely environmentally friendly manner, not only are we extracting the maximum amount of critical battery materials at the maximum purity and putting them back in the circular economy, but we are also doing this while reducing our carbon footprint. And that's a very, very impactful way of dealing with this whole issue. So lithium and battery recycling industry is poised for significant growth, right? And we as a company are contributing our bit to it, and we are the leaders today, and hopefully we'll continue to dominate this market not only in India but globally as well, right? Coming back to the entire value chain of how the lithium and battery ecosystem plays out, starting from mining, where you mine these metals, which is like cobalt, graphite, lithium, nickel. There are large mining companies that are engaged in cobalt mining, in nickel mining, in lithium mining, in graphite mining, and so on and so forth, right? The output of these mines is sometimes sold to purification companies who basically purify and make the final product that is needed for the manufacturing of lithium and batteries, especially take lithium. Almost 97% of the world's lithium supply today is controlled by China, although China does not control the mine, right? So the mined output in forms of rocks or slimes comes to China for processing. It gets refined into a final lithium carbonate product, which is what like Attero sells, and then it's sold off to, let's say, the cathode manufacturers or the anode manufacturers, depending on which metal we are talking about here. Graphite gets sold to anode manufacturers, and cobalt and nickel get sold to cathode manufacturers, right? These manufacturers then sort of, after making a final cathode product or an anode product, finally end up selling that back to cell manufacturers. The cell manufacturers are, as an example, LG Energy Solutions in Korea, SK Innovation in Korea, CATL in China, Samsung SDI in Korea, Panasonic in Japan, BYD in China, and so on and so forth, right? Uh, the scale needed to operate a lithium and cell manufacturing facility is at least a gigawatt hour, if not more. And typically, you'll see many gigawatt hour facilities popping up around different parts of the world, as and when sort of investments keep happening in this sector, right? These cells are then sold off to various battery pack manufacturers. In every country, there are many battery pack manufacturers who basically take these cells and put a thermal management software on top of it or a TMS on top of it. The objective of a TMS is that when you pack these cells so tightly together, there is thermal runaway that can happen, and you have to manage that thermal profile. And the thermal management software basically manages the thermal profile and ensures the sort of effectiveness and performance of the lithium and batteries, so to say, and the lifespan of the lithium and batteries, right? Then the battery pack manufacturers also put a battery management software on top of it, which basically enhances the lifespan and the productivity of the lithium battery. Just as a simple example, the BMS would decide, let's say, which cells need to be active out of the entire battery pack that's there. Not all cells need to be active, so which need to be active for what kind of power requirement at that particular instance, and which cells can be kept in a non-activated manner, and the entire management of that is controlled by the BMS, right? So the battery pack guys who take these cells produced by the lithium and cell manufacturers, make the BMS and the TMS, pack it all together in a battery pack, and ultimately sell it to the end user. The end user might be, let's say in consumer electronics, might be a Vivo, Oppo, Samsung, or Foxconn Flextronics, or even Acer for that matter. Or from a sort of a stationary storage perspective, might be the telecom tower battery packs. That's ones that's installed in Reliance Jio or ATC and other similar companies. Or it might go to EVs, either two-wheelers or three-wheelers or four-wheelers or the large format vehicles wherever they're required, right? And when they become end of life, they come back into the recycling stream, where because they're hazardous in nature, they need to be recycled in an environmentally friendly manner. These materials need to be extracted, and then they can go back to the anode and cathode manufacturers, thus completing the loop and reducing the dependence on mining, right? That's the entire battery value chain that exists today. And in this battery value chain, there is significant amount of technological and scientific advancement that's happening, both on the mining side to basically reduce the cost of mining, reduce the cost of environmental footprint of mining, and sort of increase the productivity of mining. On the cathode and anode side, to basically increase the performance of cathode and anode. And just as a case in point, today, if you look at the anode market, almost 99% is graphite and 1% is non-graphite materials. The world is moving towards more silica-based or silicon-based anodes, which basically more silicon you dope into the anode, lesser the graphite, more the silicon, better is the performance of the anode, right? So the world is trying to move towards a 90% graphite and 10% silicon, and there are challenges from a technology standpoint there. So that's another level of scientific discovery that's happening as we speak. Similarly on the cathode side, right? And then the cell manufacturers are trying to figure out which cell chemistry is the best. So today in the market, there is LFP cell chemistry, which is typically sort of a bulky chemistry from a weight perspective. The battery pack or cell is very bulky. The range is fairly limited. The advantage is that the cost of materials is fairly limited as well, because LFP battery cells typically have 0% cobalt, right, which is the most expensive material in a lithium and cell today, right? So from a cost perspective, LFP is extremely attractive, but from a performance perspective, LFP is not that attractive. So advancement is happening on how to make LFP battery cells or packs more sort of performance oriented and improve the performance while keeping the cost profile the same, right? LFP is typically used in buses today, and the objective is how can they be more widespread used. The second category of let's say cell chemistries today is various NMC chemistries, which basically stands for nickel, manganese, cobalt content in these cells. So if you're talking about an 811 chemistry, that would mean that out of 10 parts, 8 parts are nickel, 1 part is cobalt, 1 part is manganese, right? Or 622 would mean 6 parts of nickel, 2 parts of cobalt, and 2 parts of manganese. So NMC chemistries, from a cost perspective, they're costlier compared to an LFP chemistry cell, but from a performance standpoint, from a range standpoint, their performance and range are significantly better than an LFP cell today, right? Obviously, between LFP and NMC cells, safety issues are also there, because some of the NMC cells do have a tendency of thermal runaway, which is not that high in the LFP cells. So the advancement in NMC cell chemistry is happening on how to reduce the cost by reducing the cobalt content in there and increasing other metals instead of cobalt, right? And as well as maintaining the thermal stability of the NMC cells. After NMC cell chemistry, there are LCO cells, which is lithium cobalt oxide, typically used in your cell phones and laptops and other consumer electronic devices. And these have higher cobalt content compared to NMC cells, right? So more expensive, but better performance, so to say, right? And then there are few other specialty sort of cell chemistries being talked about, which let's say include LTO, lithium titanium oxide, which comes with its own set of pros and cons as we speak. So there is advancement happening or technological research happening on how to figure out the best cell chemistry possible. And on a related topic, there are also sort of R&D initiatives that are going on how to completely change to a new cell chemistry. So example, solid state is being talked about. Solid state essentially has no electrolyte in there. So today's lithium and cell chemistry cells, if you open up, they have the cathode, they have the anode, and a liquid electrolyte in between, right, along with the separators. The solid state essentially takes out the electrolyte that's there and ensures that there is no liquid in the cell, lithium and cells that are there. This improves the thermal stability and reduces the chances of the lithium and cells catching fire. So solid state significant advancements have happened, and we should see commercial adoption in the next few years for solid state batteries as well. The other R&D initiatives that are happening in the cell chemistry or lithium and cell manufacturing is to go to, let's say, metal air batteries, which is aluminum air batteries or other metal air batteries, which in our opinion is at least a decade away, right? And similarly, sodium ion batteries. Essentially, the objective is to reduce the dependence on sort of precious metals or sort of expensive materials like cobalt and completely take them away from the equation. So that's another level of advancement that's happening in the lithium and cell manufacturing ecosystem, right? In all of this, recycling, like I said at the initial part of our conversation, is extremely critical, and ensuring that efficient and effective recycling takes place of lithium and batteries is extremely critical. Today, the commercial plant for lithium and battery recycling that Attero operates, we are recycling all kinds of lithium and cells and battery packs and cell chemistries, right? Our process is completely automated. We do not manually segregate any cell chemistry or cell pack or based on shape and size, whether it's a rectangular cell, which is typically used in your mobile phone, or it's a cylindrical cell, which is used in various EV applications or storage applications, or it's a pouch cell, which is used in EV and storage applications. Our process is invariant to cell shape and size, right? Today, we are recycling all of these cell shapes. We are also recycling battery packs, which range from, let's say, 30 grams in weight all the way to 790 kilograms in weight, right? 790 kilograms is a bus battery, and a 30 grams is a typical mobile phone battery. Again, from a chemistry perspective, we are recycling all kinds of lithium ion chemistry, whether it's an LFP chemistry, whether it's various NMC chemistries, whether it's LCO chemistry, whether it's LTO chemistry, right? and we are able to recover more than 98% of lithium carbonate, of cobalt, graphite, nickel, manganese dioxide, and copper, and at battery grade, so that they can be directly used in the anode and cathode manufacturing setup, right? So that's what we are doing today. Happy to sort of take up any questions that you guys might have. In our opinion, this is an extremely exciting sort of area at this point in time, an area that is growing tremendously at every value, at every step of this value chain. It's growing tremendously, and there are huge opportunities that exist to create sustainable businesses and long-term businesses across the lithium and battery value chain. Thank you.